Good morning, students. In this lecture, we are going to discuss some examples of isomorphism and homomorphism of semigroup. Uh, First of all, we will see the definition of homomorphism of monoid. So let S star and T star be monoids with identity elements E and E dash respectively. That is the identity element of S star and E dash is the identity element of T star dash. A mapping F from S star to T star dash, or we can say mapping F from S to T, is said to be a homomorphism of monoids or a monoid homomorphism if following condition holds. Okay, following conditions. First of all, it is f of a star b is equal to f of a star dash. Here it is the binary operation of our codomain. Okay, here it is star dash f of b for all a b belongs to S, and f of e is equal to e dash. Okay, so this is the definition for the homomorphism of monoid. Now let us see some examples of isomorphism or homomorphism of monoids. So first is the example of isomorphic groups, semigroup. So example number 1 is let T be the set of all even integers, then show that the semigroups Z plus and T plus are isomorphic. What is here? T is the set of all even integers. Our aim is to show that these two semigroups Z plus and T plus are isomorphic. Since it is not that Z plus is semigroup with identity element 0, as well as T plus is also semigroup with identity element 0. Now our aim is to show that these two semigroups are isomorphic. So we have to define function, then after we will show that this function is 1 1 and 1 2, and also it is homomorphism. Okay. So in step 1 we will define the function f from z to t by f of a is equal to 2a for all a belongs to z. That is, we multiplied element integers with 2. Okay. Now in second step we will show that f is 1 1 function. So first of all, for that, suppose that two images are same. Okay, we have considered two different element a1 and a2, and for these two element images are same, that is f of a1 is equal to f of a2. So we get 2a1 is equal to 2a2, so we get a1 is equal to a2. This implies that f is 1 1. So this is the simple way to show that f is 1 1. Then after we will show that f is onto. Okay, how will show? For that we have considered element b belongs to t. Element b is from the t, that is the b is any even integer. We have considered arbitrary element b belongs to t. So b is any even integer. Okay, so this implies b is equal to 2a for some a belongs to z. Okay, so we get a is equal to b by 2 belongs to z, and f of a is equal to f of b by 2 is equal to 2 into b by 2 is equal to b. So for any b belongs to t, we get a belongs to z such that f of a is equal to b. So f is 1 2. Now the last step is we will show that f is homomorphism. Okay, so let a b belongs to z, arbitrary. Now f of a plus b. Okay, in both our semigroup the binary operation is addition. F of a plus b is equal to 2a plus b. Okay, this is equal to 2a plus 2b, this is equal to f of a plus f of b. These are the easy steps. Okay, so f is homomorphism as well as f is 1 1 and 1 2. So f is isomorphism. So z plus and t plus are isomorphic, that is z is isomorphic to t. Okay, this is the symbol for the isomorphic groups or semigroups. Now if we consider f of 0 is equal to 2 into 0 is equal to 0, that is, it is also monoid homomorphism. Okay, this is 0 is the identity element in both our semigroups. Now let us move to the next example. Example number 2 is, let A is equal to set of symbols 0 and 1 and consider the semigroup A star, and this is the catenation binary operation, that is the free semigroup generated by A. We have considered free semigroup generated by A, where A is single set of 0 and 1, and this is the catenation operation. And consider the semigroup A plus, where plus defined by the table. Plus is 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 0 is equal to 1, 1 plus 1 is equal to 0. In fact, plus is nothing but it is the addition modulo 2. Okay, we will know about the addition modulo. Okay, so plus is the nothing but addition modulo 2. Then show that A plus is homomorphic image of A star with catenation. Okay, free semigroup generated by A. What is our aim? Our aim is to show that A plus is homomorphic image, okay, of A star. Now what is the homomorphic image? If we define binary operation from A star to A, if we define a map from A star to A, that is homomorphism plus that is onto, then we can say that A plus is homomorphic image of A star. Now our aim is to show that A plus is homomorphic image of A star as well as they are not isomorphic, that is this map is not 1 1. So here A star dot is a semigroup with identity. What is our identity element? Identity element is the empty sequence. A star is the set of all finite sequences made from the symbols of A. Okay, here there is 0 and 1. So A star is set of all finite sequences generated by the elements of A. Okay, now if we consider empty sequence, then empty sequence is identity element for A star. We have known this, we have do this. Now A star dot is a monoid, so there is identity element, so this semigroup is monoid. Similarly 0 is the identity element for A plus. Okay, here 0 is the identity element for A plus, you can verify it. Okay, now next, now define a function f from A star to A as follow. We have defined f of alpha is equal to 1 if alpha has an odd number of ones. Okay, we have considered alpha from A star. Now the element of A star are of the form set of, what is the A star? A star is the set of finite sequences made from the elements of set A. Now in set A there are only two elements, 0 and 1. Okay, so A star contains the sequences containing 0 and 1. What is A star contain? A star contains the sequences with only two symbols, 0 and 1, 0 and 1. Okay, so if we consider alpha belongs to A star, then alpha is nothing but is this the finite sequence containing 0 1 0 1 0 and 1. It may contain all the 0, it may contain all the symbols 1, it may contain 2 zeros and 1 ones. Okay, so we have defined, how we define the function f of alpha is equal to 1. F of alpha is equal to 1 when if alpha has an odd number of ones. What is that? Means alpha contains ones, but how many odd numbers of ones? Okay, odd numbers of 1. Now f of alpha is equal to 0 if alpha has an even numbers of ones. Okay, that is if alpha is the finite sequence of 1 0 1 0, okay, and in this finite sequence if number of ones is odd, then we define f of alpha is equal to 1, and if in this finite sequence number of ones is even, then we have defined f of alpha is equal to 0. Okay, now what is the next step? In first step we have defined the function. Okay, now in the next step we will show that f is not 1 1. Why? For that, let consider 1 belongs to S star and 1 1 1 0 belongs to S star. We have considered two elements, 1 and second element 1 1 1 0. Now apply this function on this two element. F of 1 is equal to 1 because 1 is the finite sequence of 0 and 1. Okay, number of 0 is 0, number of 1 is 1, and number of 1 is odd. Okay, so f of 1 is equal to 1 by our definition of function, and f of 1 1 1 0 is equal to 1 because there are three ones, 1 2 and 3. Okay, so 3 is the odd number, so number of ones in finite sequence is odd, so f of 1 1 1 0 is equal to 1. So we get f of 1 is equal to f of 1 1 1 0, but 1 does not equal to 1 1 1 0. That is, two elements are different but their images are same. That is, our map is not 1 1. Okay, we have considered two different elements but their images are same. So these two elements are different but images are same. That means given map is not 1 1. Okay, now we saw that f is onto. Okay, so what is the ontoness? For 0 belongs to A, there are only two elements in A, 0 and 1. For 0 belongs to A, we get 0 belongs to A star such that f of 0 is equal to 0. Okay, because if we consider 0 belongs to A star, what is the 0? This is the finite sequence, and number of elements, numbers of ones in this sequence is 0. 0 is the even number. Okay, so f of 0 is equal to 0. So for 0 belongs to A, we get element 0 belongs to S star such that f of 0 is equal to 0. Similarly, for 1 belongs to A, we get 1 belongs to S star such that f of 1 is equal to 1, because 1 is the finite sequence with only 1 ones. Okay, this is some complicated. Okay, 1 ones. So f of 1 is equal to 1, hence f is onto. Now next we will show that f is homomorphism, that is f of alpha. This is the catenation binary operation. F of alpha catenation with beta is equal to f of alpha plus f of beta. Now there are four cases, and for all alpha beta belongs to A star. So case number 1 is number of ones in alpha and beta are even. Okay, number of ones, number of symbol 1 in alpha and beta are even. That is, number of 1 in alpha concatenation beta is also even, because addition of two even number is again even number. So in this catenation alpha concatenation beta, the number of 1 is again even. So there is a even numbers of ones in alpha, so f of alpha is equal to 0. Similarly, f of beta is equal to 0. Again, number of ones in alpha composed with beta is also 0, also even. So f of alpha catenation beta is 0. So f of alpha catenation beta is equal to 0 is equal to 0 plus 0. This is equal to f of alpha plus f of beta. So we get this equation. Okay. Now case number 2. Now the case 2 is the number of 1 in both alpha and beta are odd. Okay. The number of 1 in alpha is also odd and number of ones in beta is also odd. Then the number of ones in alpha catenation beta is even, because the addition of two odd number is even number. Okay, so there are number of odd numbers of ones in alpha catenation beta. Now the number of ones in alpha and beta are odd, so f of alpha is equal to 1 is equal to f of beta, and f of alpha catenation beta is equal to 0. Okay, now f of alpha catenation beta is equal to 0. Now what is our addition? This binary operation is addition modulo 2, so 1 plus 1 is equal to 2 is equal to 0. Okay, so f of alpha catenation beta is equal to 0. 0 can be written as 1 plus 1. This is equal to f of alpha plus f of beta. Now the case number 3 is the number of ones in alpha is odd and that is in beta is even. Okay, number of 1 is alpha is odd, so f of alpha is equal to 1 and that is in beta is even, so f of beta is equal to 0. Then the number of ones in alpha composed with beta, addition of even plus odd, that is odd, so number of ones in alpha catenation beta is odd, so f of alpha catenation beta is 1. Now again f of alpha catenation beta is equal to 1 is equal to 1 plus 0 is equal to f of alpha plus f of beta. All these are the simple explanation. Okay, you can easily understand this. Now case number 4, reverse of case number 3. The number of 1 in alpha is even and those of in beta is odd. Okay, so number of 1 in alpha is even, so f of alpha is equal to 0, and in beta it is odd, so f of beta is equal to 1. Then the number of 1 in alpha catenation beta is odd. Okay, I have explained above. So f of alpha catenation beta is equal to 1. So f of alpha catenation beta is equal to 1 is equal to 0 plus 1 is equal to f of alpha plus f of beta. In all the 4 cases we get f of alpha catenation beta is equal to f of alpha plus f of beta. Also for all alpha beta belongs to A star. Okay, so f is a homomorphism from A star onto A plus. Okay, we get onto homomorphism from A star to A. So A plus is homomorphic image of A star. Okay, now again f is not 1 1, f is not 1 1, so f is not isomorphism, so A star and A are not isomorphic. Okay, also it is monoid homomorphism. If we consider empty sequence, then there is number of ones in empty sequence is 0 and 0 is the even number, so f of empty capital lambda is equal to 0. Okay, so empty sequence is identity element for A star and 0 is the identity element for A. Okay, so by this we can say that this is also monoid homomorphism. Okay, where gamma is the capital lambda is the identity of A star and 0 is the identity for A. Now example number 3, let R plus be the set of all positive real numbers. What is the R plus? R plus is the set of all positive real numbers, so that the function f from R to R plus defined by f of x is equal to e raised to x for all x belongs to R is an isomorphism of semigroup R plus to the R plus with multiplication. Set of all real number with addition and the set of all positive real numbers with multiplication. These two semigroup are isomorphic with this map F. Okay, where plus and product are the ordinary addition and multiplication. Okay, So what is we want to show that our map F is isomorphism. So first of all we will show that F is 1 1, it is on 2. Then after we show that F is homomorphism. Now our map F is from set of all real number R to set of all positive real number R plus. Defined as f of x is equal to e raised to x for all x belongs to R. Okay. First of all we will show that f is 1 1. For that we have considered two elements and their images are same. Okay, so f of x is equal to f of y. Their images are same. This implies e raised to x is equal to e raised to y. Okay, this also implies that how we can show here it is y. So e raised to x upon e raised to y is equal to 1. This implies that e raised to x minus y is equal to 1. Okay, now apply the natural logarithm, we get ln e raised to x minus y is equal to ln 1. ln 1 is equal to 0. So x minus y is equal to 0. So we get x is equal to y. Okay, I have written this step directly, but this is the explanation for this step. Okay, e raised to x minus y is equal to 1. Now apply the natural logarithm, ln e raised to x minus y is equal to ln 1. ln 1 is equal to 0. So this is equal to, now ln e raised to x minus y is equal to x minus y is equal to 0. So x is equal to y. So f is 1 1. Now we saw that f is on 2. So we have considered positive real number r belongs to r plus. This implies that this is positive real number. So it is r, this r is greater than 0. Now consider x is equal to log e base r. Okay, belongs to set of all real number. Now f of x is equal to e raised to x. This is equal to e raised to log e base r. This is equal to r. Okay, f of x is equal to e raised to x. This is equal to e raised to log e base r. This is equal to r, because e raised to log e base r is equal to r. Okay, hence for each r belongs to r plus we get x belongs to r, such that f of x is equal to r. Okay, for every positive real number we get the real number from set of all real numbers such that f of x is equal to r. So f is onto. Now what we saw that f is homomorphism. For that we have considered two element x y belongs to r. Now f of x plus y is equal to f of x plus e raised to x plus y. This can be written as e raised to x multiplied with e raised to y, that is e raised to x multiplied with e raised to y. Here plus is the binary operation for r plus, okay, addition, and for r plus our binary operation is multiplication. So e raised to x multiplied with e raised to y. Okay, so we get f of x plus y is equal to f of x e raised to x, that is f of x cross f of y. Okay, so this is the simple step, you can understand easily that f is homomorphism. Also f is homomorphism, also it is 1 1 and on 2. So f is bijective map. Okay, hence f is an isomorphism from r plus to r plus product. Okay, r plus cross. So r with addition is isomorphic to r plus with multiplication. Now this similar example is example number 4, in which we have reversed the domain and codomain and also change our function. In example number 3 we change the function, okay, f from r plus to r, defined as f of x is equal to ln x, then show that f is isomorphism of the semigroup r plus product to the semigroup R plus. Here we have defined natural logarithm, okay, as a function. You can follow any steps, okay. You will show first of all homomorphism, and then after you will show that there is 1 and all 2, then it is okay. You can follow any step. So in this example I have first consider first of all we saw that f is homomorphism, okay. So our first domain is R plus, that is the set of all positive real numbers. And for this binary operation is product, okay. Now product is the binary operation for R plus, so f of x cross y, that is equal to log of x cross y. Now in logarithm we know that log of product is sum of logs, okay. So log of x cross y is equal to log of x plus log of y. So this is log of x, that is equal to f of x plus f of y. So f of x cross y we get the log x plus f of x plus f of y, okay. Log x cross y is equal to log x plus log y. This is the rule for the logarithms, okay. And here we have considered the natural logarithm. Hence f is an homomorphism. Now we will show that f is 1. For that we have considered two images are same. F of x is equal to f of y. This implies that log x is equal to log y. So log x minus log y is equal to 0. Now log 1 is equal to 0, and here subtraction of two logarithm gives the log of x upon y. This is equal to log 1, okay. Log will be cancelled out from both the side. We get x upon y is equal to 1, so we get x is equal to y. Here log cancel out means we have do this e raised to ln e x upon y e raised to ln e 1, okay. We have do this we will do this step, okay. Log cancel out means this step is hidden, okay. So we get x upon y is equal to 1. E raised to log e base xy is equal to x upon y, and e raised to log e1 is equal to 1. So x is equal to 1. That is two images are same. For that we get two elements are also same. So f is 1. Now we saw that f is onto. So we have considered any real number y belongs to R. Now consider x is equal to e raised to y belongs to R plus, okay. Then f of x is equal to log x is equal to log of e raised to y. Now log of e base e raised to y is equal to y. So for any y belongs to R we get x belongs to R plus, such that f of x is equal to y. So this shows that f is onto map, okay. So f is 1 homomorphism from R plus with product onto R with addition, okay. So f is homomorphism plus it is 1 and onto, so f is isomorphic, and these two semigroup are also isomorphic, okay. So R plus with product is isomorphic to R plus. Now there is a note, but we will discuss this note in the later next lecture, and we will discuss some example related to this note. And example number 5 is for your assignment. This is the as similar as example number 1, okay. What is the example number 5? Here we have considered set of all natural number n plus 2, 2n plus, defined as Gn is equal to 2n for all n belongs to n. Then our aim is to show that n plus is isomorphic to 2n plus. These two are semigroup, not monoids, because 0 does not belongs to this. Okay, so this is your assignment to write the solution of this example number 5. Now example number 6 is f is the map from set of all natural number with addition. Semigroup is n with binary operation addition to n with binary operation addition, defined as f of n is equal to 5n for all n belongs to n. Then f is 1 homomorphism but not onto. Okay, what we want to show that f is 1 homomorphism but not onto. Let us see. Here f is from n to n, defined as f of n is equal to 5n for all n belongs to n. First we saw that f is homomorphism. For that we have considered two natural number n, m belongs to n. Okay, f of n plus m is equal to 5 of n plus m, that is 5n plus 5m, this is equal to f of n plus f of m. These are the simple steps. So f is a homomorphism. Now we saw that f is 1 for that we have considered two images are same. For two element images are same, f of n is equal to f of m. This implies that 5n is equal to 5n. Now 5 will be cancelled out, so we get n is equal to m. Okay, so f is 1 map. Now next our aim is to show that f is not onto. Now if we consider 1 belongs to codomain, if we consider 1 belongs to codomain, then there does not exist any natural number n belongs to n such that f of n is equal to 1. Okay, if there exists any natural number n belongs to n such that f of n is equal to 1, this implies that 5n is equal to 1. This implies that n belongs is equal to 1 upon 5. Okay, but n belongs to n, so n is equal to 1 upon 5 is not possible. Okay, so we get contradiction. Okay, so by this way we can say that there does not exist any natural number n belongs to n such that f of n is equal to 1. Okay, so f is not onto, so it is our requirement. What we have shown, that f is homomorphism, that is 1 but not onto. So this is enough for this lecture. We will discuss some more example about the isomorphism, also discuss this note, okay, in the next lecture or in later on. Okay, thank you.